Okay, in this video, we're going to be doing Calc BC Problem Set number 25. The problems and a playlist are in the description below. Let's take a look. Number 1, let f be the twice differentiable function with the value shown in the table above. We want to approximate f prime of 2. And so that means we just figure out like 2 is between what in the table. And we say that f prime of 2 is approximately, you got to use the approximately equal to sign. But we can see that 2 is in between 1 and 3, so we'll just use the average rate of change from 1 to 3. So f of 3 minus f of 1 over 3 minus 1, which is going to give us negative 4 divided by 2, which is going to give us negative 2. Okay, and that's part A. No reason to ever get that wrong. We want to do that quickly and kind of move on. All right, we want to prove that f prime of x is equal to 0 for some x. This one is kind of annoying because if you look at f prime, there is no like intermediate value thing that we can immediately do to show that f prime is equal to 0. So what we're going to do instead is probably like mean value theorem twice and then intermediate value theorem once. Could we potentially have used... Well, yeah, I mean, there are scenarios where we could have used intermediate value theorem to prove that, for example, f of x equals 4, somewhere between 4 and 6. And then use mean value theorem between 0 and that value. That's not how I chose to do this, but that would have been a really good solution also. I don't know. Let's see how I chose to do it. So f is twice differentiable, which means that f is differentiable, which means that f is continuous. So we have this. Therefore, we're allowed to use the mean value theorem. And then what I'm going to do is I'm going to go from 0 to 1 and show that f prime is positive somewhere. So I will say that f prime of, I'm going to call it C1 because I'm going to do two different mean value theorems. F of 1 minus f of 0 over 1 minus 0, which is going to give us 5 minus 4 over 1, so just 1, which is positive, and that's for some C1 between 0 and 1. Now I'm going to do it again. We already know that f prime of 2 is approximately negative 2, so I'm going to use that interval. I'm just going to go from 1 to 3. So f prime of C2 is f of 3 minus f of 1 over 3 minus 1, which is still negative 2, and that's for some c between 1 and 3. Now, I know that f prime is positive somewhere and negative somewhere else. I want to use intermediate value theorem to show that f prime is equal to 0. So to do that, I need to establish that f prime is continuous, which isn't explicitly given, but it is kind of implicitly given. The reason it is implicitly given is because f is twice differentiable. So since f is twice differentiable, that means that f prime is differentiable, which means that f prime is continuous. And now I'm just going to use intermediate value theorem. So I'm going to say that f prime of C2 is less than 0, which is less than f prime of C1. And then therefore by IVT, f prime of x is equal to 0 for some x between C1 and C2, and C1 and C2 are between 0 and 6. But really the key is we just need it to be 0 for some x. There isn't really an interval given here. All right, let's take a look at the next one. We want to evaluate the integral from 0 to 3 of x f double prime of 2x dx. So this looks like integration by parts to me. So what I'm going to do is an indefinite integral. I'm going to color code it. I'm going to say that u is going to be x and dv is going to be f double prime of 2x dx. Partly because what use would it be to take the derivative of f double prime, right? Where would that get us? So u is equal to x. dv is f double prime of 2x dx. So du is just dx. And then v we have to integrate, so it's going to be 1/2 f prime of 2x, which could be problematic, but I don't think it's going to be. So let's use integration by parts, so it's going to be uv, which will be 1/2 x f prime of 2x minus the integral of v du, which is going to be 1/2 f prime of 2x dx. So we still have to find that integral. So this will give us, we still have the 1/2 x f prime of 2x. And then when we integrate 1/2 f prime of 2x, we get 1/4 because we get another 1/2 by reversing the chain rule. So 1/4 f of 2x. And then plus c, but we're actually doing a definite integral. So what I'm going to do is just like borrow everything, and this definite integral is going to be our antiderivative evaluated at 3 and evaluated at 0 and subtract them by the fundamental theorem. So let's go through and do that. So we really have to like read the table correctly here. The key is that we know the values at 6. If we didn't know the values at 6, we would be in trouble. And well, we also need the values at 0, but we have those. So when you plug in 3, you get 1/2 3 f prime of 6 minus 1/4 f of 6. So far, so good. And then minus, when you plug in 0, that first part, the 1/2 x just goes away. So you get minus 1/4 f of 0. Now we need to read values off the table. So you get 3/2 f prime of 6 is 1, minus 1/4 f of 6 is 7, and then plus 1/4 f of 0 is 4. And then you just kind of clean this up. So we get 3/2 minus 7/4 plus 1, which overall is just 3/4. Pretty good. Let's take a look at the next one. So we want to approximate the length of the curve y equals f of x on the interval from 0 to 6 with a right Riemann sum and the subintervals provided in the table. So this is actually, I want to say, kind of a common multiple choice question. I don't really think it is, but I can think of multiple examples. So step 1 is just write down the arc length, right? So it's going to be the integral from 0 to 6, square root of 1 plus f prime squared, and then dx. Now what we need to do is approximate this definite integral using a right Riemann sum. I find that it's easier for a lot of people to redefine square root of 1 plus f prime squared, square root of 1 plus f prime squared. I don't know how I read that before. So what we want to do is define a new function. We're going to say let g of x equal the square root of 1 plus f prime squared. And we can add a row to our table. I don't have space, so I'm just going to do it kind of here. So we have 0, 1, 3, 4, 6. And then what we're going to do is figure out the value of g of x, which is 1 plus the value of f prime squared, and then the square root of that. So like at 0, we're going to do 1 plus 3 squared, which is 10, and then square root of that. So we get square root of 10. Then we'll do it at 1. It's 1 plus f prime is 2, so 2 squared is 4. So 1 plus 4 is 5, square root of that. And then we'll just do it for the rest of them, which gives us another square root of 5, a square root of 26, and a square root of 2. And now what we'll do is just a right Riemann sum on that. So we're doing the integral from 0 to 6, g of x dx, approximately a right Riemann sum. So you go from 0 to 1 is 1, and then the right endpoint is square root of 5. You go from 1 to 3 is 2, and then the right endpoint is square root of 5. You go from 3 to 4, so that's 1, and the right endpoint is square root of 26. Then you go from 4 to 6, that's 2, the right endpoint is square root of 2. And I'm just going to leave my answer looking like that because, you know, it doesn't really clean up. You got those 2 square roots of 5, I guess. So you could say 3 square root of 5 and then plus that other junk. I think this is a fine answer. All right, let's take a look at the next one. We want to evaluate d dx of cosine pi x squared times f of x cubed at x equals 1. All right, so product rule, and within the product rule, a bunch of chain rule. This is really a Calc AB question. So it's first, which is cosine of pi x squared. Derivative of the second is going to be 3 f of x squared times the derivative of f of x, which is f prime of x, plus the second, which is f of x cubed, times the derivative of the first, which is going to be the derivative of cosine is negative sine of that thing, so pi x squared, times the derivative of that thing, which will be 2 pi times x. Okay, now we need to evaluate this at 1, so we'll just say such that x is 1. I'm going to show the step where I just plug in 1. So I get the cosine of pi, 3 times f of 1, and then square it, and then f prime of 1, plus, we got f of 1, and we're going to cube it, minus sine of pi, and then times 2 pi. Now, if you think this through before you do anything, you realize that the cosine of pi is negative 1, but the sine of pi is 0. So this whole second part here, because of that, just is gone. So now let's just get some values. So cosine of pi, negative 1. F of 1 is 5. So we'll get 3 times 5, but 5 squared. F prime of 1 is 2. And that's all we have left, right? So that's 25 times 2 is 50, times 3 is 150, so negative 150. All right, I think that that's it for the entire problem set. I hope this was helpful, and good luck.